A smooth, glowing weld cap is often an illusion. Underneath a visually flawless surface, critical internal discontinuities can sit waiting to compromise the entire structure. One of the most common and structurally detrimental of these defects is slag inclusion, a recurring problem generated during multi-pass flux welding processes. Normally, molten flux rises to protect the weld pool. If it fails to float in time, it becomes trapped along the fusion line. These inclusions become active mechanical weak points, creating sharp internal notches where physical stress concentrates intensely under load. To guarantee true structural integrity, inspectors must look past surface aesthetics to understand the microscopic mechanics of how these hidden inclusions initiate failure. This ASCE chart proves how slag dictates a joint's fatigue life under cyclical loading. First, 25% of the joint's lifespan is exhausted, initiating a crack at the inclusion. Then, the next 55% is consumed entirely, propagating that crack to the surface. The mechanical reality is specific. The sharpness, size, and position of the inclusion dictate the failure rate far more than the overall length of the slag line. Because sharp geometric inclusions so drastically reduce cyclic lifespan, inspection codes are calibrated to target the localized anomalies that create them. Before advanced non-destructive testing is applied, compliant visual testing requires a specific physical toolkit, a heavy-duty flashlight, a minimum 5x magnifier, a fillet weld gauge, and an undercut gauge. Illuminating weld toes with the flashlight at an oblique angle casts severe shadows across the metal, exposing surface-breaking slag or tight undercut trenches along the edge. Next, the 5x magnifier allows for a deep inspection of crater cross-sections and arc restart points. These transition zones are prime locations for localized block inclusions to hide. Fillet gauges are then deployed to check the physical bead profile. An excessively convex bead or a sharp geometric transition provides an early warning sign of trapped subsurface slag. These tools function as instruments designed to hunt down the exact geometric anomalies that trap slag and breed fatigue failure. This matrix outlines the AWS D1.1 2025 Table 8.1 visual acceptance criteria, specifically the rules governing undercut and inclusions. The code treats undercut, a primary geometric slag trap, with varying levels of severity depending on the expected loading conditions of the structure. For statically loaded connections, a shallow undercut is permissible, provided it stays within strict accumulated length limits across the weld. For cyclically loaded structures, the rules tighten. Undercut located transverse to tensile stress is strictly capped at a microscopic 0.01 inches, a quarter of a millimeter. This 0.01 inch limit is the direct result of fatigue physics. A sharp defect located in a tensile zone is the exact mathematical geometry required to initiate rapid crack propagation. While VT limits surface traps, radiographic testing reveals the internal reality. On RT film, slag appears as dark, irregular lines called wagon tracks, contrasting with the bright white circular spots that indicate tungsten inclusions. These AWS code limits represent a direct mathematical translation of fatigue mechanics into field-measurable tolerances. Standard visual inspection typically begins once the weld cools to ambient temperature, but the code mandates a hard exception for high-strength materials, like ASTM A14 or grade 100. For these specific alloys, the AWS D1.1 code requires visual inspection to be delayed for at least 48 hours after the completed weld reaches ambient temperature. This delay targets the high risk of delayed hydrogen embrittlement cracking, which can tear through high-strength alloys long after the arc is extinguished. When this delayed cracking occurs, it actively seeks out existing micro-inclusions or trapped slag as its initial initiation site. With advanced metallurgy, time itself becomes a critical inspection parameter that must be rigorously tracked. Moving from defect detection to defect prevention requires looking at the root cause. Slag entrapment is a problem of procedural geometry and fluid dynamics. The probability of creating a geometric trap is determined by the specific chemical type of flux coating used on the electrode. Basic E7018 fluxes contain calcium carbonate and fluoride, creating a high surface tension pool. This forms a convex bead with a sharp V-shaped crevice at the toe. During the next pass, molten slag flows into this crevice and solidifies before floating out, permanently locking into the joint. Understanding flux chemistry allows an inspector to predict exactly where these slag traps will form before the arc is even struck. Eliminating those traps requires a mandatory mechanical removal of all slag between every single run. This requires using segregated cleaning tools, designated for specific base metals. A wire brush used on carbon steel must never touch stainless to avoid cross-contamination. Once the slag is stripped, the operator must visually inspect the toes of the previous pass for any remaining undercut trenches. If an undercut trench exists, it must be ground out entirely. The arc force of the subsequent pass will not melt out slag trapped deep inside a sharp notch. Effective defect prevention is achieved through rigid discipline executed between every single pass. For QA/QC professionals on site, this workflow translates into a specific 4-point site evaluation checklist. First, verify the operator's amperage and travel speed against the welding procedure specification to ensure the molten pool has the proper fluidity for slag separation. Second, confirm that inter-pass mechanical cleaning tools are present, material appropriate, and being actively utilized by the operators. Third, execute the 100% visual inspection post-cooling using the physical gauge toolkit to measure bead profiles against the limits of AWS Table 8.1. Finally, cross-reference those visual findings with the NDT reports, using radiographic or ultrasonic testing to correlate surface profile indicators with internal linear discontinuities. Guaranteeing structural integrity requires merging an understanding of fatigue physics, precise geometric measurements, and rigid procedural discipline into a single, unified inspection matrix.